Hi, I'm Eric Sullivan, and this is an ALP chemistry lesson on video. This lesson is on oxidation reduction or redox reactions. And again, it's a live recording, so you may hear me, for those of you watching on video, may hear me answering questions from students in class. So I'll try to remember to repeat the questions for you for those on video. Okay, let's take a look at a reaction here. So this is one of my favorite ways to make water, and it is the reaction of two hydrogen molecules plus an oxygen molecule to make two water molecules. This is a redox reaction, oxidation reduction or reduction oxidation or redox. And in a redox reaction, electrons are exchanged. One substance is going to lose electrons, and that substance is let's show that by the example equation above. So if we look at hydrogen, what is the charge on the hydrogen? Uh, Actually, it's not plus. If it was a hydrogen ion, it would be plus. But if it's hydrogen in its natural state, what's its charge? There's no charge, it's 0. So for hydrogen, the charge is 0. But actually over on the other side, oh, there we go. Over here it is plus. So over here, now that hydrogen is in a compound, it does have a positive charge. So the charge on the hydrogen has changed. It's gone from 0 to +1. What is the charge on our oxygen on the left side of the equation? 0, right. It's oxygen in its natural state, and an element in its natural state always has a charge of 0. But when oxygen is in the compound on the right side, what's its charge? Not 2 plus. It's actually 2 minus, because it's 2 skips to the nearest noble gas and has to gain 2 electrons to get there. So it's going to gain 2 negative electrons, and it will have a charge of 2 minus. So the charge of oxygen is changing from 0 to 2 minus. For charges to change, an atom is either going to have to lose or gain electrons. So for the hydrogen, it's going from 0 to 1 plus. So that means each hydrogen has to lose an electron in order to do that. So it loses a negative electron, ends up with an extra positive charge. That's why it's 1 plus. For the oxygen is actually gaining 2 electrons because it's going from 0 to 2 minus. To do that, each oxygen atom has to gain 2 electrons. That's why it ends up with a 2 negative charge. So what happens is that the hydrogen is losing electrons, and the electrons that the hydrogens are losing are being gained by the oxygens. So there's an exchange of electrons. So the substance that's losing in this case is our hydrogen, and the substance that loses electrons is oxidized, and the charge goes up because it's losing negative electrons, it's losing negative things, so it's becoming more positive, the charge goes up. And the substance that gains electrons is reduced, and they call it reduced because the charge is going down, because it's gaining negative electrons, and so the charge goes down. So in the example above, hydrogen is losing electrons, which is why it's becoming more positive. So the hydrogen is being oxidized, and a lot of oxidation reactions involve oxygen. So hydrogen is being oxidized in reacting with oxygen. That's why they call them oxidation-reduction reactions. So its charge is going up, becoming more positive. The oxygen is becoming reduced because its charge is going down. It's going from 0 to 2 minus. So its charge is going down, its charge is reduced. So that's why they say it's reduced. Now, here's something which it seems a little backwards because the substance that's oxidized is called the reducing agent. And the reason for that is that the substance that is oxidized is reducing the other reactant. So the substance that's oxidized is the agent which reduces the other reactant. So they call it the reducing agent because it reduces something else. So it is the agent that reduces something else. And the opposite's also true for the substance that is reduced. It's actually the oxidizing agent. And again, for the same reason, because the substance that is reduced oxidizes something else. So it's the agent that causes the oxidation of something else. And a way to keep track of which is which is the mnemonic oil rig. So oil rig is oxidation is loss, reduction is gain of electrons. So a substance is oxidized. It undergoes oxidation when it loses electrons. A substance undergoes reduction. It's reduced when it gains electrons. So oxidation is loss, reduction is gain. And in terms of the agents are the opposite. So a substance that is undergoing oxidation is the reducing agent. A substance that is undergoing reduction is the oxidizing agent. So in our example above, hydrogen is oxidized, and we know it's oxidized because its charge is going up. It's going from 0 to +1. And oxygen is being reduced. Its charge is going down. And hydrogen, since it is oxidized, it is the reducing agent because it's causing the reduction of the oxygen. And meanwhile, oxygen is the oxidizing agent, and it is causing the oxidation of something else. So it's kind of backwards. So you identify the substance oxidized, it's the reducing agent. Identify the substance reduced, it's the oxidizing agent. You always have these things in couples. You always have something that's oxidized, something that's reduced. And you have to because if something is reduced, it's gaining electrons, and those electrons have to come from somewhere. So those electrons come from the substance that's oxidized. So there's always an exchange of electrons. So you really can't have one without the other. You've got to have both. Okay, so what we want to do is to look at equations and be able to identify what substance is oxidized and what substance is reduced. So what we want to do is see what's happening to the charges of the substances, the ions or compounds, ions or atoms, I guess, in a chemical reaction. So if we look at this reaction, we've got potassium reacting with chlorine to make potassium chloride. So if we look at the potassium right there on the left side of the equation, what is the charge on the potassium? Actually, it's not positive yet. Not yet. It's 0, because remember, if you have an element in its natural state, the charge is 0. So it's like aluminum foil. Aluminum foil isn't charged. It's aluminum metal. If you have an element in its natural state, its charge is 0. So aluminum foil is not charged. But if you take aluminum foil and you oxidize it and turn that aluminum into a compound, then it will have a 3+ charge. The aluminum will have a 3+ charge. But aluminum foil itself is not charged. It won't stick to stuff like a balloon. Like if you rub a balloon on your head, it'll give it a static charge and it'll stick to stuff. So stuff doesn't stick to aluminum foil because it doesn't have a charge. It's an element in its natural state. So the same as the potassium here. The potassium, the element in its natural state, does not have a charge, but when you put it in a compound, you do have a potassium ion. And what's the charge in potassium ion? Positive, +1. So we have a positive charge on our potassium. What is the charge on chlorine in its natural state? Cl2. 0, right. So it's chlorine, the element in its natural state, has a charge of 0. What charge does chloride have when you turn chlorine into an ion? Negative. And that's because it's one skip to the nearest noble gas, has to gain 1 electron to get there. Okay, so given that, potassium is going from a charge of 0 to +1. So is it being oxidized or reduced? Potassium is being oxidized. Its charge is going up. So if the charge is going up, it's oxidized. So oxidized up, oxidized. And that must mean the chlorine is being reduced. If you identify the one that's oxidized, the other one's got to be reduced. And just checking, if the charge goes down, reduced is reduced. So up is oxidized, reduced is reduced. So chlorine is being reduced. So if potassium is being oxidized, it's the what agent? It's the reducing agent. And if chlorine is being reduced, it's the oxidizing agent. So that's good. So we've been able to identify those things in our redox reaction. Now, something that is helpful to do sometimes to understand what's going on is to separate the overall reaction into half reactions. So what we want to do is pull out the oxidation half reaction and pull out the reduction half reaction. So down below, I've written the half reactions. So the first one is the potassium. These are just the equations for ion formation, which you did some time back in the course. So the potassium is going from the metal, the element itself, to 1 plus, and it does that by losing an electron. And the chlorine is gaining 2 electrons to become Cl minus. And in order for both of these half reactions to add up to give the overall reaction, turns out that the first reaction has to happen twice. Because in the second reaction, the chlorine needs to gain 2 electrons. So those 2 electrons have to come from somewhere, and they come from 2 potassiums. So the 2 potassiums, if you double that first reaction, they'll give you the 2 electrons that are going to get gained in the second reaction. So if we add up these 2 half reactions, then we'll have 2 potassiums plus 2 electrons plus Cl2. So I'm just adding up everything on the left side. And then we have the arrow, and then adding up everything on the right side of the arrows. Oh, sorry, I have that. That should be 2 potassium ions. And 2 potassium ions, and 2 electrons, and 2 chlorides. So then the 2 electrons cancel on both sides because we have the same thing on both sides of the arrow. Just like in an equal sign, if you have the same thing on either side of an equal sign, you can get rid of them. And then what we're left with is 2 potassiums plus chlorine yields 2K plus plus 2 Cl minus, which then combine to give us our 2 KCl's. So this helps us to understand a little bit better what's happening. It shows us that we need that potassium oxidation to happen twice to give us enough electrons to allow the chlorine reduction to take place. So what we'd like to be able to do is to look at a reaction and to identify the substance oxidized, the substances reduced, to also identify oxidizing agent, reducing agent, and separate out into half reactions if we can as well. So let's look at this first reaction here. So in this case, we're starting with ions. So we've got 2H plus Zn going to Zn2 plus H2. So we're starting with hydrogen ion on the left side of the arrow. On the right side of the arrow, what's the charge on our hydrogen? 0. So the charge on hydrogen is going up or down? Down. If the charge on hydrogen is going down, is it oxidized or reduced? Reduced. Reduced is reduced. So the hydrogen is being reduced, which must mean that the zinc is being oxidized. So let's check and be sure of that. So what's the charge on the Zn on the left side? It's zinc in its elemental state, so the charge would be 0, right? And the zinc is going from 0 to 2 plus, so is it oxidized or reduced? Oxidized is up. So if the charge is going up, it's oxidized. And so if the hydrogen is being oxidized, or sorry, if the hydrogen ion is being reduced, it's the what agent? It's the oxidizing agent. And if the zinc is being oxidized, it is the what agent? Reducing agent. It's just the opposite. Now let's see if we can figure out the half reactions. So we've got our 2H plus going to H2, and we need to balance with electrons. So which side should the electrons go on? If we put them on the right side of the arrow is already 0. So putting electrons on the right side will make it negative, whereas the left side of the arrow is already positive. That won't help us to balance. Right, so the electrons have to go on the left side, and we need 2 of them. Right, so now the left side of the arrow charge is 0, the right side of the arrow charge is 0. So charges have to balance. Okay, let's do the zinc now. So the zinc is going from 0 to Zn2 plus. Where do the electrons go? They have to go on the right side. So this is showing us that as the zinc is being oxidized, it's losing 2 electrons. As the hydrogen ion is being reduced, it's gaining those 2 electrons. Okay, so that's good. Let's do the next example. So actually, let's skip this one. Maybe I'll leave this one for you to do on your own. Let's go down and do the one below. Now, as we look at this one actually doesn't have ions in it. This one, they're all covalent compounds, but you can assign charges. And if you assign charges, that's called an oxidation state. So on the black periodic table that you get from the bookstore, you see the charges right underneath the atomic number, and they call them oxidation states. So for an ion, the oxidation state is the charge. But for a covalent compound, the oxidation state is the charge it would have if it was an ion, but it's really not. So it's kind of a pretend charge. You're assigning it a charge, but it really doesn't have one because it's not an ion. So the oxidation state is the charge of an ion, if it's an ion, or if it's not an ion, if it's a covalent compound, it is the charge the atom would have if it was an ionic compound. So let's look at CH4 on the left side of the arrow up above. And what charge does hydrogen normally take? Positive, yeah. So in this compound here, let's give the hydrogen a positive charge, even though it's a covalent compound, so it really isn't an ion. And over on the right side, we have hydrogen in water. What's the charge on the hydrogen there? Actually, it's not 0. It's positive 1 in the compound as well. So it doesn't look like anything's happening to the hydrogen. It doesn't look like the hydrogen's involved in the oxidation reduction. So if we look on the left side again at the CH4, if the hydrogen is +1 and we've got 4 of them, what's the charge on the carbon? What oxidation state, I should say. What oxidation state should we assign to the carbon? -4, exactly. Because we've got 4 positives from the hydrogen, so we'll have to have 4 negatives to cancel out those 4 positives. Okay, so let's look at carbon on the other side of the arrow, and we'll work that out backwards from the oxygen. So in a compound, what charge does oxygen normally take? -2. So oxygen is usually 2 minus. So how many negative charges do we have here on carbon dioxide? We've got 4 negative charges on our carbon dioxide. So what's the charge in the carbon have to be then? 4 positive. So carbon in carbon dioxide has to be 4 plus. So carbon is going from 4 minus to 4 plus. So is it being oxidized or reduced? Its charge is going up. And if charge is going up, it's oxidized. So the carbon is being oxidized, which must mean if there's nothing happening to the hydrogen, it's got to be the oxygen that's being reduced, which would make sense because it's an oxidation. So if it's an oxidation reduction, the oxygen is probably oxidizing the other compound. So we would think that the oxygen is being reduced. So if the oxygen is being reduced, what's the charge on the oxygen on the left side? It's oxygen in its natural state, 0. So the charge in oxygen, with the oxygen we're breathing in the air right now, is not charged. It's a neutral compound. So its charge is 0. But over on the right side, in the carbon dioxide, it has a charge of 2 negative. So consequently, oxygen's charge is going down. It's reduced. So the oxygen is being reduced. And if oxygen is being reduced, it's the what agent? It is the oxidizing agent. And oxygen is usually an oxidizing agent. That's why they call it, that's where the name of this whole reaction type oxidation reduction comes from. So oxygen is normally the oxidizing agent, and so CH4 is the carbon is the reducing agent. Okay. And we won't bother to do half reactions for this one. Okay. So we've got 2 equations here. So we're actually going to go backwards this time. So what we were doing before is we were looking at an overall equation and trying to break it apart to see what's going on with it and even break it into half reactions. Now we're doing the opposite. Now we are looking at half reactions and we're going to try and combine them to give an overall reaction. So what we want to do is react silver with mercury. And we want to find out what the reaction is for doing that. So in other words, down below, I've got it started here. So we're having silver reacting with mercury ion. To combine the half reactions, we do something similar to what we did with the Hess's law thermochemistry reactions in the last chapter. So what we're doing is we're looking for the thing that we're starting with, and we're starting with silver metal. So that means we're going to have to reverse the silver half reaction. And we're starting with mercury ion, so the mercury equation's okay, but the silver equation is going to have to be reversed. So let's just, I guess we can just copy, oops, the silver. Sorry, copy the mercury, not the silver. We're copying the mercury, and we'll paste it down below here. And the silver we need to reverse. So we're going to have Ag going to Ag plus an electron. Okay, so that works out. Okay, so now if we add these two, we're not going to get what we need because the mercury ion needs to gain 2 electrons, whereas silver is only losing 1. So what we need to do is we need to double that second equation. So that way we'll have 2 silvers losing 2 electrons. Those 2 electrons can be gained by the mercury. So now if we add everything up, so we've got 2Hg2 plus 2 electrons plus 2 Ags yields Hg2, 2 plus Ag plus 2 Ag plus 2 electrons. And again, we have 2 electrons now left and right, so we can eliminate those. And what we're left with for an overall reaction is 2Hg2 plus 2Ag yields Hg2, 2 plus 2Ag plus. And if you happen to be wondering why Hg has the 2 on the bottom right, it's a polyatomic ion. It's a kind of unusual polyatomic ion. It's got 2 mercury atoms stuck together, so that's why it's Hg2. So mercury is kind of a weird element. It does some unusual things. Now at the bottom here, you see we've got 0.12 V, and we have reduction potentials on the right side. So we're not going to talk about those just yet. We're going to come back to this and talk about those. So we'll skip ahead. And so again, we have 2 half reactions, and we want to combine them to give an overall reaction. And the overall reaction we want is gold with hydrogen ion. So what do you think we're going to need to do to get that? We've got to reverse the first one because we're starting with gold. We're reacting gold with hydrogen ion, so we need gold as a reactant, so we've got to reverse that first reaction. So we will have Au going to Au3 plus 3 electrons. Oops, X. And the second one, we can just, oops, I didn't put the electrons in. 3 electrons. And the second one, we can just write as is. Now, again, we need to have the same number of electrons lost as gained, and we have 2 and 3. So how can we get the same number of electrons lost and gained? Right, so we'll multiply the first equation by 2, so that will give us 6 electrons lost, and the second equation by 3, and that will give us 6 electrons gained. So now, if we add these up, we'll have 2Au plus 6H plus 6E minus yields 2Au3 plus 6E minus 3H2. And canceling our E minus leaves us with 2Au plus 6H plus yields 2Au3 plus 3H2. And again, we won't worry about the minus 1.50 V just yet. We'll get there in a moment. Okay, so now what we want to talk is voltage. Voltage is a property measured for electrochemical systems or electrical systems, and it's kind of like potential energy. It's the driving force, it's the potential. Sometimes they call it a potential or a potential difference. It's the potential for driving the flow of electrons. And electricity is really a flow of electrons. So people have done studies over time. They have studied electrochemical reactions and assigned voltages for many half reactions. So they've looked at half reactions and assigned voltages to them. They write these half reactions as reductions. So you could write them as reductions or oxidations. They decided to be consistent, they would write them as reductions. If you want the oxidation, you just reverse the half reaction. That gives you the oxidation. And so there are tables of all these half reactions, and the half reactions have the reduction potentials or the voltages assigned with them as well. Now, if you reverse the reduction, you get an oxidation. And for the reduction potential, the oxidation potential is just the negative. So you just change the sign. So it was like in thermochemistry, when you reverse the reaction, you change the sign delta H. Here you change the sign on the voltage. So again, the same way in thermochemistry, when you added the reactions, you added the delta H's. Here you add the potentials. So you add the potentials for the oxidation and reduction, and you get the voltage for the overall reaction. If it's a positive voltage, then the reaction is spontaneous. In other words, the reaction will just go by itself. If the voltage is negative, the reaction won't go by itself. And if you want that reaction to go, you'll have to apply an external source of electricity to make it go. So a positive voltage, the reaction will just go by itself. A negative voltage, it won't. You'll have to apply an external source of electricity to make it go. So here we have an overall reaction, and we've broken this down to half reactions. And in that previous reaction, the hydrogen ion didn't change its charge. In this case, it's the chloride which doesn't. Let's identify what's happening with things. So zinc is going from, what's the charge on the left side of the zinc? Of this 0. And on the right side, 2 plus. And the chloride is 1 minus on the left and the right side. And the copper is going on the left side from what charge? What's the copper? 2 plus on the left side, and it's going to, on the right side, the copper, 0. Yeah, so the zinc's going from 0 to 2 plus, the copper is going from 2 plus to 0. The chlorides are not doing anything, so the chlorides are just spectator ions. They're actually not participating in the reaction. So the reactions that are happening, the zinc, the half reaction zinc going to zinc 2 plus. Here I've just got it written as 1 plus. It should be 2 plus. So zinc going from 0 to 2 plus and losing 2 electrons, and the reduction potential, I guess that's an oxidation, so it's the oxidation potential, is negative 0.76 volts. And for the copper, Cu2 plus 2 electrons, the reduction potential for that is positive 0.34 volts. So if we add up the reactions, we will get the overall reaction. Oops, yikes. And the voltage for the overall reaction would be what we get from adding those two voltages. So if you add those two up, what do you get? Negative 0.42 volts. So would this be a spontaneous reaction? No, it wouldn't. So if we wanted to get this reaction to go, we'd have to apply electricity from an external source. So a battery, let's talk about a battery in a moment. Let's go back to some of the reactions that we already looked at here and see if we can calculate the potential for these reactions. So let's see how far back we went. No, not that far. So with the silver and mercury ion reaction, so I've got the reduction potentials written in here for the half reactions. So those are just from looking in a table of standard reduction potentials. So we left the first reaction as it was, so the potential would not change, so it would still be positive 0.92 volts. But we reversed the second reaction, so we have to change its sign, so it becomes negative 0.80 volts. One difference from delta H is whenever we multiplied a reaction in delta H, we multiplied the value of the delta H as well, but you don't for the potential. So the driving force is the same whether you do it once or you do it twice or 3 times. The driving force, which is what the voltage is still the same. So when you add those two up, what do you get? Plus 0.12 volts, which is the answer, which we've got down at the bottom of the page, just to check the answer. So would this reaction be spontaneous? Yes, it would. But it's not a very big voltage, so it's not a huge driving force in this reaction. So it would go, but it's not a reaction that goes very strongly. Okay, let's do this next one here. So this one, we reverse the first reaction. So what is going to happen to the voltage? It'll be negative 1.50 volts. We left the other one the same, and that was just 0 anyway. And so when we add these two up, what do we get? Negative 1.50 volts. And that's the answer down below as well. And it's not spontaneous. So that's a reaction that would not go on its own. Okay, so now let's talk about batteries. So if we go down below here, so a battery, otherwise known as a galvanic cell, um, galvanic based on the guy who discovered the idea, or it's named after a scientist. And so a galvanic cell, what we do to make a battery or a galvanic cell is to separate the half reactions. So with a lot of redox reactions, half reactions take place in the same container, but you can actually separate the half reactions and get one half reaction going in one container and the other half reaction going in another container. And to keep the reaction going, you connect them by a wire, and the electrons can flow down the wire to do the exchange of electrons. So you make a battery by separating the oxidation half reaction, the reduction half reaction, connect the cells with a wire. So batteries involve spontaneous reactions. And if it's a spontaneous reaction, the calculated voltage is positive or negative? Positive. So batteries are spontaneous. You don't have to do anything to make a battery run. All you need to do is connect it, plug it into whatever your device you're using, and it automatically goes. So the chemical reactions happening inside the battery, you don't have to do anything to make them go. They just go. Once you plug them into whatever device you're going to use the battery in, inside the device there'll be an electrical connection which will basically run through the device back to the other end of the battery, so the electrons flow through your device to the other side of the battery. And you don't have to do anything. The battery just goes and powers your device. But the reactions we talked about, which are not spontaneous, are where you need to apply electricity to make them go. And they're called electrolytic reactions. So an electrolytic cell is one that involves non-spontaneous reactions. And you make the reaction go by applying electricity. And this process is called electrolysis. So electrolysis is the same thing where, some people get their hair treated, their body hair treated through electrolysis. It's the same process. You're applying electricity and basically burning out the little hair follicle using electricity. So electrolysis reactions involve non-spontaneous reactions, and you apply an electrical current, a flow of electrons, to force a reaction to go in a non-spontaneous direction. Oops. So if you think about a cell phone battery involves a spontaneous reaction. It just goes. You don't have to do anything to it. It runs, it powers your device. But once your battery has discharged itself, in order to recharge it, you've got to plug it into electricity. So the forward reaction of a battery is spontaneous. The reverse reaction is non-spontaneous, and you need to apply electricity to make it work. So when you recharge a battery, you're actually doing electrolysis. So you are running the chemical reaction inside the battery in the non-spontaneous direction using electricity. There is another application of redox, and that is corrosion or rusting. And corrosion is a spontaneous reaction, and it's a process where metals are oxidized. And when they're oxidized, they go from the metal, and the metal itself, like iron in the reaction here, has a charge of 0 because it's the element in its natural state. You make a compound, and now the iron has a charge, 3 plus in this case. So the iron is going from 0 to 3 plus. It is being oxidized, and what happens is that typically the ionic compounds that form don't have the same strength as the original metal does and will sometimes flake apart, and so the structure will lose its weakness. So a car or a bridge that's made of metal, and as it oxidizes, that iron turns into iron oxide, and the iron oxide rust can flake off and doesn't have the same strength as the original metal structure did. So consequently, the vehicle or the structure will then fall apart because it doesn't have the same strength. And there are ways that you can prevent corrosion using sacrificial anodes. So a sacrificial anode is a device that, or just a material, it's really material, often zinc, which corrodes first. So in corroding, it will release some electrons and keep the metal structure from corroding. So zinc-coated galvanized nails work that way. So a zinc-coated nail, the zinc corrodes first, preventing the iron in the nail from corroding. And that is it for electrochemistry and redox.